Okay, so now is my turn to talk for the next 25 minutes or so. But I noticed that no one is going to keep me honest on the time, so I'll have to get someone to yell out at me if I go over time. No, I'm not planning to go over time. So I know we still have a few more talks to come. Xavier can throw something at me if he needs to. So I guess where things left off. So last year I gave a talk on with the exact same title, Improving Nonlinear Support in JMP, and then I've come back and I'm still improving nonlinear support in JMP. And the backstory to this is that there's some folks at Los Alamos National Labs who like to solve power optimization problems, ACOPF, and they kind of complained a lot about JMP's nonlinear support, and they said, can you improve JMP's nonlinear support? And we said, yes. Do you have any money? And they said yes. And so that's what I've been working on for the past 2 years. They kind of asked for three very high-level things. The first thing was a lot about automatic differentiation and different ways of doing AD and being able to swap in and out different AD systems and compare two solvers with two ways of computing automatic differentiation. So if you want to learn more about that, go and listen to the talk last year. As part of that work, in the background, we ended up essentially ripping out all of the nonlinear stuff that was in JMP and moving a lot of that to MathOpt interface. So at one point last year, we kind of made a change, a new release to JMP that, say, broke infinite opt, and Josh had to go and fix a bunch of things. So that's kind of, the AD stuff has kind of been done, but the next set of things were really about the difference in JMP of how you can model nonlinear programs versus everything else. And they sent me one of these examples, which is something they would like to solve, where they have a model, they have some, say, symmetric matrix, and then it's got some things in the objective that are like higher order powers. Maybe they want to do some like matrix kind of subtractions between two things, and then sum. And anyone who's kind of written nonlinear models in JMP can easily see that this currently doesn't work. One problem with it is that you had to know to use the @NL macro instead of the @objective macro. And so there's kind of these two little things in JMP that in some cases you had to do this one thing, and in other cases you had to do this other thing, and that was a little bit annoying. But the bigger problem was that this thing does not work. If you like copy paste this in, it currently errors. Because you can't have, say, vectors inside a nonlinear expression at the moment. Definitely can't have matrices. And you can't do like the broadcasting subtractions, and you can't even do sums over vectors. So their request was, can you make that work? And this is what they're currently having to do to make this work in JMP, is these kind of nasty little workarounds where to get x to the power of 4, you need to introduce a new temporary variable and then go x squared equals this new thing, and then that squared. And so we had kind of talked about in other cases, talks today, where you can write down the same models in JMP, but sometimes you have to make them a lot bigger, and being able to represent the true nonlinear form would be nicer. But it's not just Los Alamos that are having these problems. I get kind of a question on the forum, maybe not once a week, but like pretty regularly, where someone says, hey, I tried to write down this nonlinear program in JMP, and I heard it was really cool, and then I got stuck doing things involving arrays or summations or polynomials or vector valued functions. And my answer has always been, yeah, I'll be fixing that, but it's going to take a bit of time. So the good news for this talk is that this is where we're going to tell you our plan for fixing all of these problems in JMP. The underlying reason why we had these problems is that JMP historically had an affine expression object, a quadratic expression object, and then all the other nonlinear stuff on the side. So you could never build nonlinear expressions as a first-class object in JMP. You couldn't build it in the REPL, you could only build it in these weird macros, and you couldn't manipulate them or extend them or do anything like that. So what we really needed is a new nonlinear expression object in JMP. The question is, what should this be? And this was kind of not an obvious thing when we started out. And there's kind of two trade-offs here that I'd like us to kind of think about. The first one is whether we should make this expression very kind of heavy or lightweight. And what do I mean by heavy? I mean we could make a a big kind of expression graph where we recorded whether the expression was convex or monotonic, and we could maybe talk about polynomial components and quadratic components and exponential components, and we could add a lot of stuff into that. Or we could keep it very lightweight and just say, here is the expression graph, and this is a sine node, and that's all you get to know. That's kind of on the mathy side of things. On the actual Julia programming side of things, we need to kind of think about this typed versus untyped trade-off, where we could go kind of into the Julia type system and do lots of complicated stuff there, or we could kind of keep it as simple as possible. So what we did is we went away and looked at how other people have solved this problem in the past. One that probably a lot of people here have seen or used is this symbolics.jl package, where like jump, they have an @variable macro, and you can kind of declare variables, and then you can, I don't know, say sine of x or x squared, and it builds an expression graph. Under the hood, they chose to represent this as a set of nested structs, where we're kind of using the Julia type system to add information to our nodes in the expression graph. But it's also a bit what I would call heavy in some places, where the fields in the nodes sometimes contain, say, dictionaries and like, are these arguments sorted, and some other information that is not just what is the expression. And it's kind of sitting somewhere on this typed, untyped trade-off, where the nodes themselves are typed, but some of the arguments are just any. And so that's one choice. Maybe at the extreme end of using I won't say abusing, but using the Julia's type system is maddiff, where everything gets effectively put into the signature of the type. So if I had an int plus an int, then the type signature of expression 2 would be int plus. And then if you wanted to nest that expression, you can kind of you keep kind of stacking these things in it, and it quickly blows out. The benefit is once the Julia compiler can kind of compile that expression, it's very fast to evaluate. The downside is it doesn't really scale beyond a few terms. But this is not a problem that is just faced by people in Julia. So how to, say, nonlinear optimization packages in other languages handle this. One option is Gravity, which is a C++ modeling tool that actually gave a talk in JumpDev 2018, which you could go and have a look up. I think it's still on YouTube. And this is in C++, but I would call it typed and heavy, because it's got a lot of stuff in here that is useful if you're, say, working with nonlinear programs, but you kind of have to carry it around. So they've split out the linear, the quadratic, the polynomial terms. They've split out whether the term is convex or monotonic. And one nice thing about Gravity is it's very fast. So at Los Alamos, they're building these big ACOBF problems, and Gravity is maybe 50% faster than Jump on some of their larger problems. I guess the trade-off is this is in C++, and some of the techniques that they use in C++ from a kind of typed, untyped choice don't necessarily translate that well to Julia. The other option in Python is Pyomo, which is a very popular modeling language similar to Jump, and they support lots of nonlinear expressions as well. And it's kind of hard maybe to do a direct comparison between, say, the Pyomo and Julia, but it's kind of similar to the symbolics thing, where they've got these specialized nodes in the expression graph with a little bit of stuff in there. So I didn't want to put the slide up and get accused of misleading benchmarks, but we went through and tested these four different things out, and they all have, I guess, pros and cons in different types of problems. Sometimes they're fast in one problem and slow in a different problem. And so we kind of stepped back and said, Julia has some unique things about its type system. We want to write down really large expressions. Is there any other example, maybe not from a mathematical modeling perspective, but is there anything else in Julia that works with large symbolic expressions of trees? And the answer is yes, just the Julia expression object. Right? So it can parse all of a Julia file, and it's actually building an expression tree of functions and stuff in it. I mean, it's not mathematical optimization, but it's effectively the same thing that we need. And the Julia expression graph has a head, which is a Julia symbol. In this case, it's a call node, but it could be a different type of node. It could be a ref or an and or something like that. And then the arguments to their functions are just a vector of any. So it has a symbol as the head and then a vector of any. And we kind of know that this works for really large problems in Julia because everybody here is using it and no one is complaining, right? And there's maybe some work that has gone in to make this data structure of a symbol and a vector of any be efficient. So we thought rather than trying to match what, say, other mathematical programming libraries have done, why don't we try and match what Julia has done? So in terms of this heavy, lightweight, and untyped trade-off, I think we're actually choosing to go towards the lightweight end of things, because all we provide is a symbol and a vector of any, and then a kind of untyped thing, because you only have a vector of any. We're not trying to put any specialized type information into the nodes in the expression graph. So effectively, this is going to be the new design of nonlinear expression in JUMP. A head and then a vector of any, and it's just totally inspired by the Julia expression. What does this look like in practice? In JUMP, you can say, so there's a PR in JUMP, if you go and have a look, where you can kind of try and test this out. If you use that branch, it's not currently released, you can say, using JUMP, I make a model, I make a variable. Then in the REPL, you can call sign of x, and we overload all of the basic nonlinear functions in Julia for JUMP variables. And now y is a nonlinear expression. The head of this sign of x is the symbol sign, and then the args is a vector of any with just one element of x. And then inside JUMP and inside MathOpt interface, there's effectively a big lookup table of how you can convert the symbol sign into something that's useful for doing function evaluations and derivatives and stuff like that. But at the user-facing end, it's just a very simple data structure that's easy to work with. Thinking back to all of the problems that Los Alamos had with the current syntax, how do these translate to the new nonlinear expression object? One thing is that you can build up these nonlinear expressions outside of macros. So in the REPL, I can just write down x plus x to the 3 times sine of x to the x. And I can write down the same thing inside a macro, and now there's kind of no difference. So I no longer need to use the @nl expression to build nonlinear expressions. I can either build them in macros or outside of macros. I can also do vectors and matrices and things like that inside macros and outside of macros. So here's that same example of x to the 4 dot minus x to the 3 summed. In this case, I haven't shown you the big printout here because it actually ends up being a very large scalar expression with a very large number of terms, and so it kind of went down the page too much. But at least at a high level, you can kind of now write down these things as you would want to, rather than having to find all of these hacks and introduce new variables into the problem.
So you're relying upon at least vector operations that you're going to let Julia scale up.
Yeah, so Miles's question for the YouTube is, how does this kind of work? And the answer is that inside Julia, there are generic overloads for how you can multiply 2 matrices. And essentially, they boil down to scalar additions and multiplications. And so we haven't written anything special for how you can multiply 2 matrices of JUMP variables. We just let Julia's generic dispatch kind of keep going until it finds the basic scalar plus and multiplication. So this could end up being this kind of expression swelling problem where it builds a very large expression, and then we have to go and deal with that later. And maybe in the future we could think about how to have some vector valued nonlinear function where we could explicitly write down a matrix to the 4 rather than some scalarized version. Another interesting thing that kind of plops out and is directly related to what I just said is function tracing. So now if you write down a Julia function and you don't type the input, then if you call that function with a JUMP variable, we just try and use operator overloading to try and build that nonlinear expression. So here I create a function myfunc, which is 2 to the y plus x above y to the power of minus 2.3, and it builds that expression. Previously, if you've used jump and you've kind of written user-defined functions, you had to register them, where then you had to kind of register it and either use automatic differentiation to compute the derivatives, or you had to manually provide those. Whereas now you can just plug in the x and it builds the expression. But there's also a way to still register user-defined functions if you know you have a complicated function and you can provide the explicit gradient. In this case, there's a new @register macro that returns you an object, and that, instead of tracing the function, now just stops and says, okay, here's where I'm going to stop, and I'm not going to try and evaluate it any further. So the bit in the discourse post at the start of the talk that I had kind of blocked out, and this person was saying, I had this problem and I have trouble with sums and products and stuff inside nonlinear expressions. This was the model they were trying to write. In this case, it's got a nonlinear constraint. It's got a bunch of these functions, these kind of nasty things. And to write this model down in jump at the moment is not very nice. You can kind of do it. And in that thread, we kind of went back and forth for a while. But we had to introduce a bunch of new variables and a bunch of other things, and it was quite messy. Whereas now this just works. Because when the LHS appears as a function, and P and Q are variables, and even if P is a vector of jump variables, we do this function tracing thing, we build the expression, and it kind of seems to work. So I would expect a lot of models that people have tried to write down in jump in the past and maybe gone to a different tool because it gets a bit complicated or a bit nasty should suddenly be a lot nicer to work with. Josh also hinted about this. Because we now have a first-class nonlinear expression object inside jump, it's now extendable. And so he's already worked on integrating these new nonlinear expressions into infinite opt. And he already presented the benchmark, so I'm kind of repeating things here for the people in the room, but maybe for the YouTube video in the future. We built 3 different types of models in infinite opt. One of them took 7 seconds to run, one of them took 46 seconds to run, and one of them kind of just errored with a recursion depth limit. And now these things build in the new nonlinear expression branch of jump, and they're much faster. So I think this is a win all around. And we have some other benchmarks that show that this new first-class object compared to jump's previous code is about the same speed. So we kind of haven't lost anything in performance. We've gained some in some other places, and the interface is a lot nicer to work with. For people who are more interested in how this actually works under the hood, maybe if you're writing nonlinear solvers or trying to connect the JSO stuff into jump, there's this nonlinear expression object at the jump level, and there's a corresponding scalar nonlinear function at the MOI level. And they're exactly the same form. They both have the symbol as the head and then a vector of any as the arguments. And so now a solver like IPOpt is going to declare that it supports nonlinear constraints because it says, I'm going to add a constraint of this scalar nonlinear function in, for example, the interval set. And we could also, we had a talk on complementarity before. A solver like Path is going to declare that it supports the vector nonlinear function in the complementarity set. So at the MOI level, this kind of nicely integrates with all of the other stuff we've been doing. One issue that you may have been thinking along as I've been talking is this expression just has like the symbol sign and then a vector of any as the arguments. That's nice to represent it symbolically or as the expression, but how do I actually like compute with that? How do I compute derivatives or evaluate the function? And the answer is that inside the MOI.nonlinear submodule, there's a whole bunch of tools for working with these expressions and turning them into oracles that you can compute with. So the actual implementation of adding this new function support to IPOpt is like 100 lines, because all it does is it reads in the expression graph. It says, hey, MOI, can you return me oracles to compute the function and the gradient and the Hessian? And then here you go. So I guess to summarize what I've been talking about over the last 20 minutes. The pros and cons of this current design, I guess the pro is that it's simple, right? So we chose the simplest structure that we could, which is the symbol is the head and the vector of any. It's really lightweight, so it's kind of up to you to do what you want with it. There are solvers like alpine.jl, which needs to know about monotonicity and convexity. We've decided not to help with that. So the first thing Alpine's going to have to do is read in this expression graph and then turn it into some other format and add a bunch more information. So that's one of those trade-offs on that light versus heavy thing. Another pro is that this is already working and implemented. So we could potentially do other things, but this is the one we've kind of gone with, and it's there. And in our benchmarks, it seems to perform just as well as the current version of Jump. The reason being that actually Jump is doing the same thing at the moment, just in a different form. So in the @nl macro, what actually happens is we're parsing the Julia expressions as the Julia expression type, where now we're passing it as this jump.nonlinear expression, which is effectively the same thing, it's just got a different name. We've also moved all of the automatic differentiation stuff out of Jump into MOI, so when IPOpt says, I want to convert this expression graph into an oracle, that's all there. And then the kind of slightly weird thing about this, and Miles hinted this at maybe this is a Jump 2.0 thing, is that our current plan for the release is that it's just a feature addition. So if you write down @nl objective or @nl constraint, everything will still work. But if you write down one of these new constraints, you kind of will get the new nonlinear expression. The downsides to this is that for a while there could be two ways of writing down nonlinear expressions in Jump. If you write the @nl, you'll get the old way, and if you write the new way, you'll get the new way. And that could be confusing in the documentation or online if people are looking at old tutorials that use the old syntax, and we're trying to suggest the new syntax, and there are some very subtle differences between the two. So we need to think about that transition if or when we merge the new work. So I guess our next steps for where this is going. First, we need to fix a couple of printing issues in how those expressions get printed. Maybe we can simplify some of the printing so we don't get such large expressions from time to time. We also just released a bunch of generic number support to Jump for linear and quadratic functions, so we need to think about how to integrate that into the nonlinear stuff. And then this really needs some testing from people on their problems. So Josh has been doing a bunch testing it out with InfiniteOpt, but if you're solving nonlinear programs in Jump, I would be very happy if you tried out this new thing and said what you liked about it and what you didn't like about it. So the best way to engage with that is to go to the Jump GitHub repository. And if you just look in the PRs, there's one that it says, work in progress, new nonlinear interface. And so add that branch, try it out, and then let me know what you think. So thanks very much. So I didn't run over, I didn't steal anyone else's time, so we have a few minutes for questions.
Thank you for the nice presentation. I guess you already mentioned it when Miles asked the question during the talk. I was wondering if you can elaborate a bit more on this. Currently Jump, in the current version, is a bit tricky to work around user-defined functions that are vector valued. And I was wondering if this new branch, like in the new way of doing things, if it has made it any easier. In the documentation, there's like a section on how to kind of work around the interface.
Yeah, so the question was, lots of people have tried to use vector-valued user-defined functions in the current version of Jump, and the answer is we can't really do that. There is a workaround where you can memorize the evaluation of the function, but it's kind of these hacks. In the new version, if you register a user-defined function, it must be a scalar, like it must return a scalar. So we haven't fixed that in that sense. But if you use the function tracing approach, and your function that you've written down actually returns some nice algebraic form, then this calling myfunc, if it returns a vector, will now return you a vector of these nonlinear expressions, and then you can use them in other places. So it solves the problem if you can trace it. It doesn't solve the problem if you need to register it.
So not every function can be traced.
Yeah, so Miles' point was that not every function can be traced, and so yes, there will be some models that benefit from this, and there will be some that are still stuck. Anything else, or up back?
Yeah, so one issue Convexus had with the operator overloading and such is when there's base functions that are products, like hcat and vcat, where it's hard to define a method to say dispatch to my special implementation if I'm a more arguments like that.
Yes, so the question is, with this operator overloading approach, some Julia functions like hcat or vcat that have a variable number of arguments are very hard to overload and intercept. And the answer to that is we do not. We only overload a very small subset of the Julia functions, so just the basic nonlinear primitives like the trigonometric functions, log, exponential. There are things like the inequalities. So you want to be able to write down, like in jump, if else x is greater than 0, a or comma b. You can't write this down outside of the macros at the moment because we haven't overloaded variable greater than or equal to variable. So there is still some, this is the documentation issue for releasing this, where there are still some very subtle differences in what you can do inside the macros and what you can do outside the macros. And we need to think about how to communicate that well.
When you generate this expression that you currently, let's say that I have a constraint that is like 1 to 2000 x squared, some kind of weird nonlinear function. Like if you say you have 1,000 constraints of this like a strange nonlinear function, are you generating, let's say, 1,000 copies of the expression for the variable when you calculate it, or can you store? Are you storing, let's say, like a for loop that says like this is like 1,000 times this constraint?
So the question is, if I wrote down in jump, I wanted to write down a vector of nonlinear constraints, or like a for loop of nonlinear constraints. Do I, and it's for I equals 1 to 1,000, I'm going to write x to the I less than or equal to 1. Do I make one symbolic representation of that constraint and then plug in the data? Or do we just make 1,000 expression graphs? And the answer is we just make 1,000 expression graphs. If you go and look at my talk from last year, we talked about a new way of doing automatic differentiation, where you can then parse the expression graph and realize that there's actually a bunch of repeated structure, and then you can handle it there. So on the solver side, we can deal with that cleverly. But on the user side, we're just going to do the dumb thing and make 1,000 copies. Okay, we have perhaps one more question.
Back on the second last slide, you're pushing the AD to the solver. Didn't quite get.
Yeah, so this is more, I guess, where the code lived in jump or MRI, as opposed to when it got needed to be computed. So the solvers always needed an oracle for evaluating the function or the gradient. Previously, Jump's automatic differentiation engine was inside jump.jl. So jump, when you wrote down a jump model, it computed the gradient first and then passed that to the solver. Now we're computing the expression, passing that to the solver, and then the solver computes the derivatives. It's just a small structural change in where things are rather than anything like math or solver related.
What do you mean the optimization? You said the math optimization interface, or the like IPOP will be computing its own?
Yeah, you mean the solver wrapper or the solver?
The solver wrapper.
Solver wrapper.
Yeah, maybe in the interest of time we will call it there, and we can talk about this afterwards. So thanks everyone.